All right, so molecular orbital theory, this is the closest theory to kind of the truth. So it's kind of the most accurate, most precise. And so the drawback of it, if it's the most accurate, why wouldn't we just use it all the time? Well, in order to do this kind of stuff, you need high-level calculations. And so these are most often done on computers. You can do them, the very simple ones you can do by hand, but anything even remotely complex is going to have to be done by a computer. And so what molecular orbital theory kind of builds on this idea of hybridization, that these orbitals are going to mix together. And molecular orbital theory takes it one step further, and it says that orbitals in a molecule do not belong to a single atom. Electrons in a molecule do not belong to a single atom. They all belong to the entire molecule. So instead of having atomic orbitals, you have molecular orbitals. And to find these molecular orbitals, what's done is what's known as the linear combination of atomic orbitals. So some linear algebra, sometimes abbreviated LCAO, right? Linear combination of atomic orbitals. And so again, just like valence bond theory, it goes back to this idea that electrons are three-dimensional waves. And so if you have things that are in phase, these waves will join to make a bigger wave, and this is what's known as a bond. And so when things are out of phase, you have the opposite. They cancel one another out, and this is what's called in molecular orbital theory an anti-bond or an anti-bond. And so here's just this little diagram. Right, so you have two s orbitals, right? One s and then another s, and so they can combine, and they can do two things. One, they can be in phase and form a bonding orbital, or they can be opposite phases and form an anti-bonding orbital. And so you can see they still call them sigma. So sigma is still a sigma bond. And then up top, you see this anti-bonding orbital gets sigma star. So it's pronounced sigma star. And so this is an anti-bonding orbital. So this is a sigma anti-bonding orbital. And so you can redo this same thing with p orbitals. Notice in this case, we're looking at the px orbital. So these guys face each other directly. And so they can go into a bonding orbital or a new bonding orbital, or they can form an anti-bonding orbital. Right? And you can see how this looks like a bond and this does not look like a bond. And so the kind of little tricky thing here is that p orbitals, just like we saw in valence bond theory, can still form sigma bonds. So that's the px orbitals. What about the py and the pz orbitals? Just take a look at one of them here. And so they can mix as well to either form a bond or an anti-bond. But in this case, right, there's not direct overlap. So they're pi bonds, right? So this is a bonding orbital, and this is an anti-bonding orbital. And so pi orbitals can either make sigma bonds or they can make pi bonds. Cool.